Hi everyone, my name is Boros and I'm a principal architect at Percona. Today we are going to talk about copying data over high latency network links, and the title of my talk is Going the Distance. I heard that conferences are great for networking, so I brought a networking topic. So about me a bit, I'm a principal architect at Percona. My focus and interest is mostly automation and performance tuning for databases, especially MySQL. All my examples will be MySQL related where it's applicable. And among others, I worked at Dropbox and some microsystems. But the things we will talk about will be applicable not just to MySQL, but to practically anything. So we will talk about what is a difference between a long distance copy and a non-long distance copy. We will talk about measurement and benchmarking. We will talk about TCP/IP, and then we will talk about how is this applicable to backups. So what are these long distance copies? When are we calling a copy long distance? So long distance simply just means more latency and not necessarily less bandwidth. So if we have two geographically distant locations, the bandwidth, the latency between them will be naturally high, simply because we have physical limit of the speed of light. For example, between the West Coast and Europe, the latency will never be less than 100 milliseconds, no matter what. So why do we need these long distance copies? In every DBA's life, there is a point where you have this task to either create a disaster recovery environment, and in order to do that, initial clones need to be created, so the data needs to be copied there. Another option when this can happen is moving to the cloud or migrating off the cloud. In that case, between the two providers, the distance might not be geographical, but the latency between these two networks might be high. There can also be disaster recovery testing when we need to do practice exercises where the large amounts of data needs to be copied, or the application might need read replicas in remote regions. For example, the data is served by a local copy of the database, but the writes are collected to a central place. That's also not unusual to see. So first, let's measure how badly network throughput is affected by latency. So when we want to copy data between A and B, what we are mostly interested in is throughput. Right? We want to copy with X megabyte per second, or megabit per second, or gigabyte per second. Right? So in the measurement setup, actual databases or actual data is not needed to validate the methods of the copying. In the measurement setup, I used AWS, but the lessons learned are generic. I tested data transfer within the same region when both instances were in US West 2. I tested the data transfer between two distant regions, which is EU Central 1 and US West 2. The problem itself is not database related. And we tested with T2 micro instances. So the results are reproducible in the free tier if you want to do that. The difference with larger instances will be that they have more consistent speed, simply because the larger instance you get from a cloud provider, in this case Amazon, the more dedicated network capacity you will have with it. So the more consistent results you will have. But the difference will be so big between the regions that it's valid to show even with this setup. So let's cover some of the theoretical background. So in case of TCP, when the connection is already established, when one of the endpoints, when the client sends a data packet, the server needs to acknowledge it, right? This is why this acknowledging mechanism and what guarantees all of our data to arrive makes TCP not great over high latency links. So if the link latency is high, you can imagine that the data packet is sent super fast, let's say within far less than 1 millisecond, then it waits on the network more than 100, and the acknowledgement is sent back also within 1 millisecond, the processing time. It also needs to wait 100 milliseconds for the other side to arrive, and then it can continue. So by default, TCP is not great over high latency links, but typically for copying databases or for copying actual data, TCP's property of not losing packets is needed. But the sliding window mechanics are here for us to help. That means that in the drawing on the right-hand side, you can see that several packets are sent before receiving acknowledgement for the first one. So in this case, 4 packets are sent before receiving the acknowledgement for the first packet. We also have various mechanisms to help this with, like selective acknowledgement. So selective acknowledgement means that we can receive one acknowledge answer for multiple packets, and these are adjusted dynamically. So what you need to check for these parameters to tune is the buffers in the kernel, like the vmem and rmem for TCP especially, and if you have the window scaling on. So by default, Ubuntu has it on. So let's try an iPerf on the same region. So iPerf is a tool for benchmarking networking. Here I have an abbreviated version of the output. Basically, you can start a server in the most simplified case like this, and you can start a client which connects to the server on a port. And at the end, you will have by default the benchmarks are 10 seconds long, and at the end it will give you a throughput result. So between these two micro instances, which can have up to 1 gigabit network speed, in this 10-second benchmarks, I measured 883 megabits, which is very, very close to the gigabit. So this kind of met the expectation I have. Throughout the talk, there will be a bunch of abbreviated iPerf outputs. So, but I provided the comments always. So if you want to play around with that, you can. But iPerf is like the de facto standard of network benchmarking tools. So how about we copy in the same region, but limiting the window size? In this case, what I supplied differently is I supplied the -w parameter for the client, and this means that the unacknowledged packet sizes could be only 100 and 1,400 bytes. So in this case, instead of 800 megabit, I only got 15. And so the difference is drastic. With the small window size, if we go back to the drawing, a large window size will mean more parallel senders before receiving the first acknowledgement. So more data packets sent before receiving an acknowledgement. And when I set a window size that is less than the MTU, it means that it will be almost serialized. The almost is important here, but it will be almost serialized how we transfer data over that link. So very promising. The window size affects the data transfer a lot, even within the same region. So we can say that, hey, in this region, that this must be happening over the high latency link, right? So if I try to measure the same thing on a high latency link, I will get results very close to this, simply because I'm waiting for all the acknowledgements. I'm doing nothing to transfer data, but only wait for acknowledgement. That is the exact same thing that is happening over a high latency link. So very promising. So what do we have? So between different regions, US West 2 and the EU Central 1, you can see that I actually masqueraded the IPs with 1.2.3.4. So these are not real testing IPs, but I get 64 megabits per second. So if I check out the previous one, 15 megabits per second, 64 in this case, it's not as bad as if I would specify a very small window, but it's pretty close, right? We can say that probably we have the same issues here, right? So what can we do? We can increase the buffers. We increase the buffers, more parallelism. If we go back to this one, if we increase the buffers for the window scaling, we will have more parallel send. If we have more parallel send, we will wait less for acknowledgements. So we can increase our throughput, right? So that's what I would have expected. But after tuning those parameters, I only got a slight increase, okay? So these are not great results, actually. There is a slight but consistent difference. Requesting and you can see here that with the -w I could also request a large window. In this case it's 8 megabyte. So requesting larger windows at the iPerf level doesn't make much difference because we already had selective acknowledgement and window scaling. So these are the parameters that would really help, but these are kind of defaults in modern Linux distributions. And also these tunables are available on a per connection basis if the application supports it. So in order to use a large window size, like in case of iPerf for a single data transfer, you don't need to size the global buffer accordingly. You don't need to increase that buffer for every single transfer because it's not beneficial for everything. Okay. So how about parallelism? So what if we achieve this parallelism by using multiple TCP streams? So the idea here is if I go back to this drawing again, we will go back to this drawing a lot. The idea here is that I spend very little time sending the data. I wait a lot for the acknowledgement to arrive. So if I'm doing more sessions in parallel, one of the sessions will spend very little time sending the data. The other session will spend very little time sending the data and wait for the things. But these little data packets will add up, and it will and sent in parallel. So the acknowledgements will be received in parallel as well. So on multiple streams, we will have a better utilization of our pipe throughput-wise, while latency will be similarly not good. So back to parallelism. So what I'm talking about is that in the previous test, we had a single TCP connection, so the source sending data to the destination. In the tests which I'm going to show, we will have multiple TCP connections. So multiple senders are sending data to the destination. In iPerf, you can do this with -p4. And in order to be able to compare, the iPerf output will be very different in this case, because it's actually multiple thread sending, and you will have statistics per thread. And what you need to check is the sum. So in this case, I left the previous result, the single-threaded result, in place as well with the large window size. So in this case, with 4 threads, we could get 210 megabits. With 6 threads, we could get 317. And with 16 threads, we could get close to half a gigabit, right? We had 800 or something within the region. So on 16 threads, we can go as high as half of that, despite the huge latency between these instances we have. So this is great, right? So this is the way to go. In order to use these parallel TCP streams, you will need a different source port for each of the streams, but not necessarily a different destination port. As you saw it in case of iPerf, I'm using 16 parallel streams, but those 16 parallel streams are sent to a single port. So what is often mistaken by people is that in order to use 16 streams, I need 16 ports. There are implementations that need 16 destination ports, but if the listener party implements the I/O multiplexing properly, one port is enough. So the destination, you will need a source port for each stream, but you don't necessarily need a different destination port for each stream. So seems like parallel streams is the way to go. And it can be useful even locally. So in case of modern high-performance network controllers, you cannot saturate them with a single TCP stream, simply because they have multiple interrupt channels for both transmission and receiving. So you need, in order to utilize, for example, a 40 gigabit NIC, typically you need to use more than one TCP stream. And another case when this is useful, if you are using IPsec. IPsec is very taxing on a single stream, but you can achieve good throughput on the encrypted connection with parallelism. Okay, so what options do you have for copying an existing backup? If you would like to copy an existing backup, I'm talking about you have a set of files to copy, right? The backup is made, you have the files, and you want to copy them over multiple TCP streams. Normal methods could be like SCP to copy to a different destination, or tar pipe to netcat, but these are all single streamed options. So there is a utility that does exactly this. It takes a set of files and it copies it for you over parallel TCP connections. And it's called BBCP. And it's using SSH for the control channel. And it seems like SCP. It looks very much like SCP. At the first glance, it seems like somebody took exactly the SCP interface and coded and implemented parallelism and coded BBCP. But it's not exactly SCP. And the important thing is that control traffic is encrypted because the control traffic of the copy is over SSH, but the data transfer is not. So the actual data chunks that are copied is not encrypted. How to set up on Ubuntu 20.04. You can clone it from this Git. This is a fairly old utility. Build it with make, copy the produced binary to the path, and verify that it works with the -- version command. So here is an example. How would you use that? So issue the BBCP command, specify the number of parallel streams, specify a port range. In this case, it's important that this implementation needs a port for each stream. And we are copying the directory called testd recursively to another machine. There are some caveats. It doesn't handle tilde for a short notion of home directory. Again, it's like SCP. It seems like SCP with different options, but it's not. The BBCP binary must be in the path of the receiving machine. So how it works is it uses SSH for the control channel, And on that control channel, it will actually start up BBCP processes on the ports you specify. So the BBCP binary must be in the path, so it must be accessible for it. Bidirectional communication is needed, meaning that the receiver will connect back to the sender. And again, can't stress this enough, the data is not encrypted, only the control channel is encrypted. Okay, what options do we have for extra backup? Right, at the beginning I told you I'm mostly interested in MySQL. Extra backup is Percona's hot backup tool for MySQL databases. So what options do we have here? So by default, XB stream in extra backup will emit a single stream that can be copied. So we can copy that single stream over SSH, Netcat, SOCAT, or anything like that. But that will be inefficient on high latency link. The network copy will often be the bottleneck. In previous jobs, I implemented various parallel copy methods between the high latency links, and I saw improvements as high as 20 times for the parallel copy. So this is something worth investigating if you have this issue. There is an out-of-the-box solution for parallel copy, which is using XB Cloud and object storage. So XB stream will emit a single stream that could be copied again. Netcat and SOCAT and the likes are copying a single stream, but network copy is often the network copying, or the single stream is often the bottleneck. So XB Cloud is coming to the rescue. It will copy your backup to an object storage, and you can copy within the object storage to another region, and both can be parallel. So one of the example commands that we can use with the XB Cloud, this is from XB Cloud's documentation. So we can do an extra backup with parallel 10 and stream XB stream. So we get our stream from the database in parallel, and then we pipe it to XB Cloud, which can also be parallel. And in this case, the parallelism is uploading the backup to S3. So how many put requests, how many parallel put requests will it do for S3 in order to copy your data? And you can then, when your data is in S3, S3's region copy is actually parallel. So you can just use the AWS command line to do AWS S3 copy from the source bucket region 1 to target bucket region 2, recursive. And the thing is, the caveat here is that you need to be verbose about the region, right? So you might have the region in the URL, but you need to specify source region and dash dash region as the destination region, and then you can copy it like this, and you can specify how many concurrent requests should that copy do. One thing here is that if you copy data like this, the filters, if you are using include and exclude filters, some of them are interpreted on the client side. So make sure that your copy is not hitting any client side limitations, because that can slow things down pretty significantly, right? So in summary, you can use XB Cloud to copy to an object storage. It can be S3, it can be MinIO, or it can be anything that implements the S3 API. It's very common to have that. You can copy the data to another region of the object storage, or you can specify a remote region for XB Cloud right off the bat. You can restore locally from the target object storage. If you want to create like a copy from that backup, we want to create, for example, a replica from that backup, the restoration process will be local. And it's important that this example was AWS and S3, but XB Cloud works for other object storage too. And you will get the same high throughput as you would get with BBCP or what you saw with parallel iperf before. Okay, so what if you don't have this option available? You don't have an object storage, but you still want to do this. And in this last section, we will take a bit of a look under the engine cover, like how can this be implemented. So this is the how does it work part of the talk. Any stream can be read in chunks locally, meaning that I'm opening the stream for reading. I read 64 megabytes, do something with that 64 megabytes or any chunk size, or 100 megabytes or 200 megabytes. And these chunks read afterwards, they can be processed in parallel. Especially this talk is about sending them over the network, but they can also be compressed in parallel or encrypted in parallel. You can do with anything expensive with these chunks in parallel. And the tools, all the tools mentioned earlier have similar mechanics inside. So how does it work? We have a source of the stream. Then we have some kind of sender which will read the things in chunks. Like here, we are reading the first chunk. It's the first, square labeled with 1. Then the second and the third and the fourth and the fifth and the sixth, right? So we are reading these chunks. We are sending them over this cloud in parallel. We receive them in very likely a different order. The different order is very important. Then we need to put the stream back together, which assumes the same order again. So in order to do this, we need to open the stream and read these bite-sized data chunks. So we will be able to process them in parallel. Okay, there is no out-of-the-box solutions for it, as far as I know. So there is nothing like parallel netcat. The stream can be read, and again, the stream can be read in chunks locally, and it can be sent over the network in parallel. And those chunks can be processed in parallel. We have a simple Python example here if you want to toy around it. You can see that first we are importing the subprocess, which is for executing commands within Python. And then we are defining a data chunk class, which has the data and the sequence number. So here it's important, if we look at that, to store the number of the chunk together with the data, because we can use that information on the receiving end to assemble the stream again. So imagine if we wouldn't number this, but they would be equally sized data chunks received in a totally different order, which we don't know. Right? If we number them, we know in what order they need to be processed. So we are defining a data chunk class, which has the data and the sequence number. The role of this class is just to tie them together, the data and the sequence number. Then we can open xtrabackup with --backup and --stream equals xbstream. And standard out and the standard error will be a pipe. And we have a chunks list above that, which is just an empty list. And then we can append to the chunk list a data chunk, and that data chunk, the data chunk needs a data and the sequence number, right? Needs the data and the sequence number. So for the data part, we are reading the standard output of the xbstream process, where the stream will be emitted, and we are reading 64 megabytes in this example. I spelled it out like this so it's visible that it's 64 megabytes, and we are assigning the sequence number 1 to it. Then we read another chunk, other 64 megabytes, and then assigning a sequence number to it. So at the end of the day, we will have a bunch of chunks, right? And you can see that that indeed we have 64 megabytes worth of data in a chunk. So after that, So how it would work is we would get a bunch of chunks, like 20 or 100 or whatever, and then process them in parallel. Then we would get another 20 or 100 or whatever. And how large the chunk and how many are we getting at once depends on how much memory are we able to use for this process. So I hope I could shed some light on the inner workings of how a stream can be parallelized with this drawing and this bit of an example. Let me know if there is interest in an open source like parallel stream copier, and I might make something for the next conference. Thank you very much for listening to me, and time for questions.